Welcome everyone. This is the first of the two lectures which will be given by Professor Christian Maes on non-equilibrium calorimetry. I ask all the students, particularly all the students who are present here physically and also have joined online. I hope they will actively participate and interact with the speaker. Please remember that he has put in a lot of time and effort to pitch the lecture at the level of master students and PhD students particularly. So yeah, I hope that you will, you like to get interrupted, Chris, right?
Sure.
Yeah, so he likes to get interrupted. Please unmute yourself, ask questions. Okay, so yeah, Chris, you can start.
Thank you. Hi. Does the sound okay? Okay, so welcome everybody and thank you for being here. Indeed, it will be the subject of non-equilibrium calorimetry, and as already mentioned, of course you can interrupt me at any moment. You don't need to. Relax. I'm here also the whole week in case you want to talk about certain things. Be happy we have this opportunity. Having said that, I would like to go right ahead without much ado and without much introduction or motivation and just get immediately inside the subject. However, just to make sure we are, as they say, on the same page, I will try to start in equilibrium, actually. Simple calculations for equilibrium. Perhaps that will also be able to warm us up in a way, and I hope that many of you will find it a pleasure to recognize things. Oh, let's see what happens. Right? So I would like to start with maybe the simplest system for statistical mechanics, which is a two-level system. Usually in two-level systems, one thinks maybe about qubits and quantum mechanics, but I take even the simpler version, if you wish, the classical version of the two-level system. So what do I have in mind? Well, two levels, so it means that I will write here or draw two levels, and the meaning is that a particle or many independent particles can be in two states, which we call 0 and 1. And we imagine that there is an energy difference, a positive energy difference, to go from 0 to 1, which is epsilon. And we also imagine that these particles, these two-level systems, are immersed in a bath, a heat bath at temperature T. I will also, just to make sure, I will denote by beta the inverse temperatures, putting the Boltzmann constant equal to 1 in most of what I am saying. If you're not sure whether I'm doing things correctly, you can always ask me, of course, but that will be my lazy assumption to just take beta equal to 1 over 2. So that's the physical setup a priori for the first example for calorimetry in equilibrium. And intuitively, it is a very nice equilibrium in the sense that it is described in a whole usual heat bath ensemble or the canonical ensemble of equilibrium statistical mechanics. So when we are asked to compute the heat capacity of such a thing, then the first physicist reaction would be what heat capacity, right? Because there are, in fact, as you learned, many heat capacity depending on constraints on what you're fixing. Now, if I'm fixing here this energy level height, it really means that I'm implied, for example, that I am at constant volume, right? So if I'm doing here the computation of the heat capacity at constant volume, which I will denote CV, it will be a function of that temperature. Of course, it will also be a function of epsilon, but that I am not writing. And the manipulation we have learned in school is that we should take the average energy and we should take the derivative with respect to temperature. I will come back to why that is so. But we'll just continue with the formula that we are used to. Now, what do I mean by this energy? Well, with this energy, I'm actually meaning the average energy for this ensemble that I have here. And so that means that here is energy 0, here is energy epsilon. So what I have as average energy is epsilon times the probability that my particles is in the state 1, right? That's what I have to do. And so what do I mean by the probability that I am in the state 1? Well, that is the usual equilibrium ensemble at temperature T. And again, without much explanation, I hope perhaps some of you will recognize the usual ensemble, that the probability to have 1, I have to think of it, is like 1 over e to the beta epsilon plus 1. And we can as well add the probability in the 0 state. It would be like 1 over e to the minus beta epsilon plus 1, right? That, or the probabilities, the stationary equilibrium probabilities, the thermal probabilities to be on the upper or on the lower side of the two-level system. And here you see this, that it is governed, in other words, by the product beta times epsilon, this dimensionless quantity, which, for example, if you're at very high temperature, remember that the beta is 1 over the temperature, would mean that at very high temperature, the beta is like almost 0, so you get like typically 1/2. So this is always a check you can do. And if the beta goes to infinity, then you will like to sit in the 0 state, the ground state. So these are the typical checks you would like to do. So in other words, what you do for the heat capacity, you obtain the probabilities of occupation. Basically, here we only have to worry about the higher level because that is carrying the epsilon. And we then take the derivative with this temperature. Perhaps as an exercise, if you have never done that, you can do it. But I hope that you will find the result. And the result looks as follows. So I'm plotting here. I hope it's still visible.
Yes.
Is it still visible? So I'm plotting in the horizontal axis the temperature. And there I am just forgetting the subscript V, that I'm fixing the volume by writing the heat capacity in the vertical direction. And this, I'm not giving any units here or anything, but the behavior is more or less like that. Actually, this is much too flat, but okay, somehow like that. In fact, this little heap or this peak, or this peak that I'm having here, that's called a Schottky anomaly. Okay, that's just a word for that I'm not going to speak about, but it is somehow important for understanding why you would be interested in heat capacities. Because already here, this peak tells us something about this epsilon. In fact, this peak happens at the temperature where the beta epsilon. So this is at the temperature. Sorry, this is at the temperature which corresponds in unit of temperature to epsilon. You know what I mean? So that is where the peak is happening. All right. Maybe for the rest, I would like to give you another exercise, if you do not mind, is that I wonder if somebody can explain to me, by the way, that if I take the integral from 0 to infinity, so I integrate over the curve the temperature, so I integrate this in not quite the curve, but I take the heat capacity and then divide by temperature, then this will be an integral, just a mathematical exercise. The formula that you will get is not completely trivial, right? I mean, if you take a derivative with respect to temperature, it's trivial to do, but it's not like a very simple thing. It's just with exponentials and so. But from physicist's point of view, you don't need to do the integral. That's sometimes useful, no? Sometimes by physics insight, you can do a mathematical integral because I know that this will be equal to the logarithm of 2. You understand why, somebody? Anybody who wants to dare to say something? So maybe I'll help you here. You remember perhaps also that the heat capacity, more fundamentally, not enters via such a formula, but in fact enters via the relation, which is the defining property That is that if you give a certain temperature difference to your system, what is the heat that flows in? Or what if given a heat, how much you increase the temperature, right? And the capacity is like an inertia for that. So you give heat and you see by what it is increasing its temperature. You remember, for example, the standard for water between between 14.5 degrees and 15.5 degrees Celsius, you need per gram of water 1 calorie. That's the kind of 4.186 joule. That is a very high number for increasing the temperature of water, 1 gram of water by 1 degree Celsius. Now, so that is kind of the operational basic definition of heat capacity. But there is another relation that you know, and that is called Law 2.1. You know, Law 2.1, that's the Clausius theorem. And the Clausius theorem is saying that for a reversible transformation, if you divide dq over t, it is equal to an exact differential, which we call the Clausius entropy. Maybe you know also that formula from basically an introduction to the second law of thermodynamics. But now if I combine these two equations and I do a reversible transformation and I divide the left-hand side and the right-hand side, I get as the result that the delta Q over T is equal to the Ct dt over T. And so if I take the integral of that, I just get the total change of entropy. But if I integrate from 0 into infinity the entropy, I get the entropy at infinite temperature minus the entropy at 0 temperature. But the entropy at 0 temperature is 0. In fact, that is a non-trivial statement. It is obeying what is called the Nernst postulate, so-called third law of thermodynamics in the version of Max Planck from the beginning of the 20th century. So the entropy at 0 is at absolute 0 is 0. So in fact, what I'm writing here is log 2, and log 2 is just the entropy at infinite temperature. Okay? So that's why we can do the integral without thinking to do the mathematical manipulations, as it is simply the entropy at infinite temperature for a two-level system. And for a two-level system, you know how to do entropy calculations simply. It's just the number of degrees of freedom, which is log 2. And that's another insight we are using already from the 19th century, that in fact this Clausius entropy, which is defined, which is basically constructed by Clausius by reversible transformation, is in fact also the Boltzmann entropy, which is related to the counting of degrees of freedom. So that is basically, okay, without too many details, how you can think, how you deal with the equilibrium, statistical, mechanical, heat properties, and the two-level system. That clear? So far, so good. So maybe if you wish to have a bit of fun tonight, you can actually do the calculation of this heat capacity to see that my drawing is not extremely bad, to check that the peak is indeed around in temperature units epsilon, and in fact, perhaps even to check whether your Mathematica program is running fine, to do this integral so that you get the logarithm of t. So let me now yet do another calculation, which is very similar, but for another type of system. I just want to do that because in what follows in the rest of the lectures, we will be dealing with various models, perhaps. And so it's good to have, instead of a discrete model like we have here, also a much more classical model, which is in a continuum description. So that is, I have chosen to be extremely simple here. So the model that I chose to do here is just a harmonic, just a pendulum basically in a heat path. Again, an ensemble, of course, in the canonical ensemble. And here we are dealing, okay, I will call it the position, but if you do not like the word position, you can, for me, also replace it with speed or velocity better. But for the moment, I will just write x to be the real value, where I have a self-potential, ux, just a potential, which is given by the parabola, just the usual kind of harmonic self-energy. Okay, so now I would like again to compute the heat capacity, as you very well know how to do, and I will follow exactly the same recipe as for the two-level system. What else? And so what I have to do is to calculate the heat capacity as for constant volume, and I need to know the average energy. And here the average energy is a little bit, I mean, the same strategy, but a little bit a different calculation. Namely, here the average energy E would be like, I will denote these brackets. You know, these brackets will denote expectations, statistical expectations in the canonical ensemble, so we can be very explicit, at least I hope. I will do an integral from minus infinity to plus infinity dx, and it's an average of u of x. And so what I have to plot here is the rho equilibrium T rho of x, which is the density, equilibrium density, and this equilibrium density for this harmonic system is of course given by the Boltzmann-Gibbs factor, so it's beta k2x squared, and then there is a normalization that is probably something like square root of 2 pi divided by beta k, if I'm not mistaken, something like that. That is the canonical ensemble for that system. And then you plug that in, and because the ux is just x squared, basically, what you're doing is to compute the variance. But the variance, yes, please.
What is k in the denominator?
The k here, that's the same k, the spring constant. Spring constant, thank you. Yeah, that's a spring constant. Yeah, basically that allows me also to give another comment that is not extremely essential for the moment, but still something that you may want to recall. That is that such a heat capacity that we have here could also be measured by the variance of the energy. But let me not do that for the moment. So after taking the derivative with respect to temperature, it would be the variance of the energy. Anyway, I hope that you will forgive me that I'm not doing this calculation here, but basically I have to take the variance of this Gaussian, so it's basically something with beta and k, and then you get the value of t over 2 times k. So this is not Boltzmann constant, by the way. Boltzmann constant that is equal to 1. The k is just a spring constant, so that is kt over 2. That doesn't sound correctly to me, actually. It should be 1/2, no? So the computation I probably was wrong. You should check. So I'm talking about the energy. Is it kt over? Yeah, maybe there is a k here, actually. But just a scaling factor. I'm not sure if there is a k or not. But should there be a k? Okay, you'll figure it out for yourself. I don't know what it is. But in any way, you get a constant, you get the heat capacity, which is just a constant, right? It is no longer varying in time, in temperature. It's basically k over 2, if I'm not mistaken. And as you learned also in school, probably that is typical for such systems. This is like the basic toy for understanding the equipartition theorem, or the law of, maybe you remember the law of Dulong-Petit for crystals, where you have, of course, not just x squared, but you could have various dimensions, 3 dimensions, in 2 directions. So you would have the typical scenario that you would predict that heat capacity of a crystal would just independent of temperature, right? Which is wrong, we know, because at low temperature such effects enter, quantization enter, and in fact you will have that postulate for a perfect crystal which is obeyed. But we don't care too much about that for the moment. I just want to give you an example of hopefully a correct calculation of a heat capacity. All right. Now, is there a question about that? So that's the way you do it. In the canonical ensemble, you just calculate heat capacities for constant volume by taking the derivative of the energy with respect to temperature. Right? So let me repeat that it's not that the heat capacity is defined by that formula. I already mentioned that it depends on what you keep constant, whether you keep the volume constant or whether you keep the pressure constant. But I also would like to emphasize again that the basic formula starts here, in the definition of an inertia which relates temperature changes and heat flows. That's where it all starts, right? And of course, you can relate it to entropies and all that. That's not important. Not the point. Okay, now another issue that I would like to add as an observation after having said these two examples is how could it be that the heat capacity, which has to do with, well, heat, right, which has to do with fluxes, with energy transfer, intuitively, how could it be that it does not depend on the dynamics or on other aspects on the dynamics, right? So let me try to specify that question a little bit. Let us again look at, so this is a postscriptum for the two-level system. So if I do this two-level system, I can say, well, the occupation, the number of particles in level 0, it will change in time. I'm just going to take an equation which is probably not too far from the truth, and I hope you will find me agreeing with me. So I write how this occupation number at the 0 level, how it changes in time. Well, I mean, how can it change in time? It can change in time because you're depleting the 0 level, so there is a minus sign. And now I need a letter for a minus. So I will write here, let me write here a gamma, because there are not so many letters around. So there is a minus gamma NT. And of course, there is repletion because you're falling down the emission for the plus level, for the 1 level. So you're adding here a delta NT of 1. So that is the basic equation for understanding these formulas dynamically. But now let me make a trivial remark. And a trivial remark is that having said that, I can of course write this as minus gamma. I just put it in front. I'm not doing much, right? I put it in front and I just repeat. But now, of course, since I have put it in front, I get delta over gamma, actually with a minus sign, NT1. I didn't do anything except I put the gamma out of it. But clearly, I'm saying trivial things, but important things it will turn out. Clearly, for having the stationary behavior, it seems that it is not so much the gamma that is important naturally. You have two constants, but you want to put it to 0, so only one constant matters, right? But the constant that then matters in this way of doing it is really the delta over gamma. That is the important thing. So in other words, even though you have done your best perhaps in calculating the depletion rate for the 0 level, it will not enter except that it is the ratio of delta over gamma which will enter. And so let's try to remember that, and let us try to ask later in our lives, which is not too long actually, why it is or how it could be that gamma does become important when it does not become important. Okay, but it's a remark that we would like to remember. In fact, the same postscriptum can be added for our harmonic system. So what is the equation which corresponds to this kind of, I don't know how you call this equation, it's just a kind of master equation, right? A linear master equation. Here also we have what is called certain master equation. We will come back to that. It is a Fokker-Planck equation. Let me write it for you just next to the harmonic system because I could go to that line. So here the equation that is related to the Fokker-Planck, so for the harmonic system, is that if I look to the derivative in time of the density, so now this rho t is what you would have. This is time, no? This is temperature. The rho t would be the time-dependent density, which eventually perhaps will evolve to the equilibrium one. But let us not worry about that for the moment. I'm just writing it. And basically, this is a probability density. It satisfies a continuity equation. Think about it like this rho tx is, don't think about it something very abstract. You can think of it as a mass density. And so there is the spreading of this mass of these independent particles that each one sit in the harmonic potential, right? So then I will write I will write a continuity equation, which is like the usual one-dimensional thing. So I will have here a current, and that will be equal to 0. That's a continuity equation, right? And then for the current itself, Jk of x, well, what do I do phenomenologically, but of course also in a way very correctly? It is basically given by the force divided by something like, okay, the mobility. So what is the force? Well, okay, so there will be a constant in front. Maybe I'll write it, 1 over mu something. This is a similar thing as the gamma, actually, similar to that. And then what is the forces that we have here? Well, there is, of course, the force, which is the minus u prime of x. So this prime is the derivative with respect to u, with respect to x of u. That's the force, right, in Hamiltonian or in Newtonian sense. And then, of course, you have to take into account the mass that you have there, which is rho t of x. But there is another term here, because, you know, it's like, think about all these particles that are moving in this heat bath at a certain temperature. So there is also a force which is Fickian. Right? So there is the diffusion force, which is also playing a role. And this diffusion force is something which is in fact related to the temperature in the simplest cases, and which has the derivative with respect to x of the rho t. I will perhaps explain more where this comes from, but perhaps you have seen such things before if you're doing phenomenology of diffusion or things like that. I really have. Yes, please.
Mu is mobility.
Sorry, Karen?
So mu is mobility or the friction?
Yeah, the mu would be something like mobility, but do not take it too serious for the moment. It's basically how you negotiate force and current here.
It should be multiplied, right?
Perhaps, but if you wish, define it differently. I mean, I don't care too much about it. Forgive me. So the point I wanted to make is that, in fact, if you have stationarity, so if you would like to look at the stationary equilibrium, then of course it could be that you only need that the divergence of the current is 0. Right? But we can do better. We can even take the current equal to 0. In one dimension, in fact, there's not much difference. But okay. Right? In one dimension, there is no much difference, right? But if you are having the current equal to 0, it means that this bracket must be equal to 0. Okay? And this bracket equal to 0, I hope that this is exactly giving me that solution. I don't know, but I hope so. Gives me exactly that solution. And my point that I wanted to make, an analogy with the point I'm making here, is that the thing that I do not know what it is 1 over mu, which I thought is something like a gamma, but maybe wrongly so. Doesn't matter. Right? Again, it doesn't matter. So it's a very similar remark that I made before for the two-level system. Again, I have a kind of redundance and constants when I go to stationarity for obvious reasons mathematically somehow. I wonder why do I even mention that, but hold on. I mean, we will come back to such points later where we are moving away from equilibrium. Okay, so this was the remark I wanted to make here. All right, now I want to continue, and I would like to ask not only this postscriptum, but I also would like to understand how can we get a bit of a more dynamical understanding of this heat capacity. The reason is that, you know, in the end, I would like to move to non-equilibrium calorimetry, where the non-equilibrium does not so much refer to the fact that I have a time-dependent phenomena. I will mean by non-equilibrium steady non-equilibrium. So I will have stationarity, except that there will be not something so easy like currents equal to 0. I may have currents going on. I will come back to this point later, but it's good that you already meditate on these words. So my non-equilibrium will not refer to time dependence, rather it is steady, except what you will call the breaking of detailed balance. So this is what I want to explain a little bit better now. Okay, but the question first of all is, in what sense can we imagine that dynamics matters? All right, so let me go back to my two-level system and try to see what is the dynamics that I can invent, somewhat corresponding to this kind of master equation, but let me go on the mesoscopic level. Okay, on the mesoscopic level of really understanding the stochastic dynamics. So there are many things I'm saying that, in fact, or if I would have to explain them, would require many more words. But I'm skipping over things. But if you want to interrupt me, it's fine. No? So let us erase some of that at least. Okay, so remember our two-level system. So our imagination is basically the following. We are thinking about transitions where the particles, which are, say, sitting on the zero level, would go up, would go all the way to that level, and they do that by getting an energy of the amount epsilon x. And when we have particles which are sitting on the higher level, our imagination would say it corresponds to an energy which is outgoing, or epsilon. Somehow being the imagination that the whole thing, the heat bath and the system together have a kind of conservation of energy, and what happens is an exchange of energy. Right? And this exchange of energy, the rate at which this exchange of energy is happening, of course, depends on that amount of energy, but it will also depend on the temperature. Okay, so now I would like to open the brackets for a moment to introduce you to, for those who have never seen that, to introduce you to some rather standard elements of Markov processes. So I will not give you a course in Markov processes, but very limited things so that we can understand what you're doing. Okay, so let me open the brackets. Literally, here is my open bracket, and let me tell you something very simple about what is called a Markov chain. So by a Markov chain, the chain I'm using here for the fact that I will be using discrete time. So in a Markov chain that generates trajectories, but in discrete time, which are stochastic, which are random, and they look as follows. So here is the time. It is discrete, so you measure it in, I don't know whether you measure time in days or in years or in seconds. Maybe you don't care, so I will measure it. And on the vertical axis, for example, for my two-level system, I can put my two states. So this is the one state and this is the zero state. And maybe at time zero, I will dare to use another color. I hope it is sufficient. But so maybe at my zero time, I am in the zero state. And then at time one, I feel very good. I'm still sitting there. But maybe at time two, I am in the one state. At time three, I'm again in the zero state. Again, at time four, I'm in the one state, etc. So that is a little bit of a strange trajectory, perhaps, but a trajectory in discrete time for my two-level system, right? So what I have to tell you basically is, I'm saying it is a stochastic process, so I have to tell you the rules. Rules are not like deterministic; they are given by a probability. So by transition probability. Right? So in general, well, let me not go too general, but we have states x, which here, for example, which here would be 0, 1. These would be the states. In general, of these states, you should think of more like either a coarse-grained description from starting from a classical system. You could think about two chemomechanical configurations of a protein or something like that. Or if you want to start from the quantum side, you should really think how this stochasticity is generated by things like the Fermi-Dirac golden rule, where I compute these transition probabilities by overlap of wave functions. Right? You have heard about that, that's fine. Okay, anyway, so here we have a 0, 1. And if I am doing the updating, what I said is that I need to consider transition probabilities, which I will denote by Pxy. The Pxy has the meaning that it is the probability that at time n plus 1 I am in x, while at time n I am in y. Sorry, no, I am in y. This is my convention while I start from x. So my convention in the notation is I go from x to y. So what do I mean by this xn? Well, that is exactly what I have in blue here, this trajectory. That is the x at time n. That's my random trajectory. Okay. The fact that it is Markov, this word Markov, means indeed that the updating is always like momentarily. I don't need to know anything about the further past. The present is enough to update me for the next day. Right? That's what is called the Markov property. It's kind of forget everything before that. Right? Anyway, that is the transition probability pxy, which is supposed to be given. I'm not giving it yet. I just want to introduce you to some structures. So now, when I give this pxy, it means that I'm giving you what is called, with a kind of confusing terminology, I'm really giving you the stochastic matrix P, which has the matrix elements, which are, I'm sorry for this strange notation, but it's a matrix with these matrix elements. That's called a stochastic matrix. It doesn't mean that it's a random matrix. It means it's a stochastic matrix, and that means that if I sum over the, I don't know whether you call this rows or columns, but if I sum over the y, that should be equal to 1, right? And on the other hand, these pxy should all be non-negative. That's the definition of a stochastic matrix. So it's a square matrix which has these properties. That's called a stochastic matrix. So it is basically in this stochastic matrix, you get all the information to simulate these trajectories. You just start somewhere, you throw your coins, and you go on. Right? That's how you get the Markov chain, nothing else. All right. Now, before I go on with my two-level system, I want to, in my bracket here that I'm still having open, I would like to discuss something which is related, which is important for us physicists, as it is related to time reversal symmetry. By that I mean a following. So given this updating, I can understand perhaps that there may be something like a stationary behavior. By that I mean the following, that it could very well be that I'm going to take it as an assumption. Of course, there are theorems and all that that will assure that it is true, but here I'm just going to assume it. I assume that if I just look at the probability that x at time n is equal to y, given that at time 0 is equal to x, that this will converge, in fact, exponentially fast as the discrete time goes to infinity, to a particular probability law, which is a stationary one, and I assume the uniqueness and existence and positivity, strict positivity of all that. Okay, so this is an assumption. It is not always true. If you want to do the mathematics, I would suggest that you look up things under the heading of Perron-Frobenius theorem. And it's a good idea to do that, actually, to look up why that is true, because it's just an easy application of linear algebra. Right? It's this kind of Markov chain, you understand there is a lot of linear algebra, right? That will play. Because, by the way, this thing here, this can be seen as the end power of this matrix. I hope you can, maybe you see that or you feel that. Maybe it's sufficient to feel it and not to see it. You see, if I do updating this n here, suppose it is 2, I first go to time 1 and then to time 0, but that's like multiplicative with sums. So it's really like matrix multiplication that I'm doing. So this probability here is really a matrix element of the stochastic matrix. I take it to the power n or n plus 1, I do not know. And I look at the matrix element x1. And that's how you come in the neighborhood of these linear algebra techniques, and in particular of this theorem, famous theorem of Perron-Frobenius for understanding the conditions, because they are needed. They are called irreducibility and aperiodicity, but okay, doesn't matter now for the moment, to go to a unique stationary distribution exponentially fast. Okay, good. So if we assume that, we have the notion of stationarity. I'm saying stationary, I'm not using the word equilibrium now. I'm just saying stationary. Why stationary? Well, stationary in the sense that obviously if I start from this row S, it will be invariant in time. right? Because it's asymptotically reached, whether it is xn here or xn plus 3, who cares, right? So it is stationary in the sense that it is invariant under this discrete time updating. So we have a stationary distribution, meaning the following, that if I initially at time 0 draw my initial state from this distribution, then in fact at every moment, time 3, time 4, I will get the same statistics. And that's what it means to be stationary. I'm not saying equilibrium because that I reserve for a higher purpose. For a lower purpose depends on your case. Okay? But let it be clear conceptually, that is what I call stationary. You can typically get it from asymptotic in time behavior. And it is invariant, not in the sense that there is no dynamics. Things keep moving, of course, but the statistics is invariant. The density has the probabilities for seeing the various states does not longer change. It's important to keep that in mind. Okay, now, let me now start, in fact. And if I say start, you can put it in quotes in the sense that, what does it mean to start? At every moment, I have the same distribution. So, no need to say that there is a beginning. So let me suppose that the x0, and in fact, all the xn, has the distribution according to rho s. I will just write it like that in a kind of abbreviated way. So at every moment, I am distributed with rho s. So I'm in the stationary regime. I have waited long enough. I did my simulation. I came back last week and so, and it's a finite, whatever. I'm stationary. In fact, if it is stationary, I can as well take the n in z, meaning also for negative times, because I can shift my origin to minus 10,000, even to minus 10 million. I can put it at minus infinity. Right? So I have a stationary sequence. So I'm really in this stationary world. And that allows me to define the time reversed sequence, which is at time n, it is the one at time minus n of the other. So it's another process, right? Yn is x minus n. I'm still doing mathematics here for the moment, but it is going into a direction which will be important for us for non-equilibrium. So it's very simple. I just do the movie reversal. So the xn is like, you think of this trajectory as like the movie. It's stationary at every moment. It's a very boring movie, actually. The statistic, well, maybe there are movies like that. So at every moment, you see basically the same thing as if drawing from the same scenario, same thing. But nevertheless, for every trajectory, I can take the time reversal. And that's what I mean by Yn. And obviously, also the Yn is distributed with rho s. Because x minus n is distributed with rho s. Okay, now what I'm interested in is to ask what is the probability that Yn plus 1 is equal to x, given that Yn is equal to y. So I'm asking for the transition probability. It's not so difficult to see, actually, that the Yn is itself a Markov chain. And I'm just asking, yeah, what is its law? What is the force, you could say? No, it's like in Newtonian mechanics. You have take a Newtonian free fall or whatever mechanical problem of Newton with a certain force. And you would ask, if I take the movie of that and I reverse time, I see a new movie, right? What is the force then in that movie? But for Newtonian mechanics, do you know the answer? What will be the new force? So here's the question. I'm not speaking of calorimetry. I take Newtonian mechanics, I take the movies of, I don't know, planets or whatever, or things that you throw to each other. And what I do at a certain moment, I reverse the velocities. At the last time, I reverse all the velocities and I let them move backwards in time. So the question is, what is the force that now will govern the movie? It is the same force. That's called time reversibility. Right? That's called time reversibility of Newtonian mechanics. Okay, but let us see what is the force here, or what is the change here. So for that, we are using the most important proposition in statistics. You know the most important proposition in statistics? Maybe we differ, most important. So, but I tell you, my most important proposition is Bayes' theorem. So that would tell us that this is the probability. So I'm skipping one line here. So I'm putting this to that side. So that will be x minus n equal to y, given x minus n minus 1 equal to x. And then I have to multiply here with rho s of x divided by, what is it, rho x? Yeah, I guess it's that, rho s of y. But I'm just applying Bayes' theorem, right? The definition of conditional probability, basically. Does that require an explanation more, or is it fine? So what I'm using in Bayes' theorem is that the probability of an event A given B is equal to the probability of the, that's how Sherlock Holmes solves murder cases, no? Probability of A given B is the same as the probability of B given A times the probability of A divided by the probability of B. If you want to know what's the probability that A is the murderer given evidence B, you should imagine, given that he was the murderer or she was the murderer, what will be the probability of the data I see? And then there are some a priori's that I have to take into account, like how much I like the murderer and how much I can trust the evidence, or those things is the evidence. Right? But that's how you do police investigations, and that's how Sherlock Holmes proceeds with the investigations. So I'm using Sherlock Holmes' method for solving this physics problem here, is to understand what is the law of the time reversed trajectory. Okay, so that is Bayes. I will erase Bayes, but let his name be blessed. So now I find that this is going from x to y, because this is -1 and this is, this is the usual updating. That's why I did the whole thing. So this is just the p that I have somewhere here. I can plug in. So this is the p for going from x to y, rho s x divided by rho s y. And I have assumed, I hope, that this is strictly positive. I don't have any problems with probabilities that become 0 in the stationary distribution. So what I find is that if I denote just for fun, this probability by a q, this is for the y process, this is for the forward and this is for the backward process, so to speak. You see that I have that the reversed process has a transition probability which is not quite the same. Not quite the same. But there is a case where it is the same. And that's the case. So we have that indeed. So can I erase this computation to get a bit of space? Am I going too fast or too slow, or in the back? People are all happy, still following a bit? Okay, well, interrupt me, then I'll slow down. At some moment, I will make a major mistake. So be careful that you follow, because otherwise we go all the way around, right? Okay, so I will erase, well, not much actually. So we say that we can say now that the stationary process is reversible or time reversible, but I will just abbreviate it as reversible, that the stationary distribution does not see the arrow of time. That's what we mean. It just satisfies time reversal symmetry. I'm always saying the same thing. If and only if, actually, if and only if the way to update from y to x times rho sy is equal to bxy rho sx. That's called, in this context of Markov chains, a version of what is called detail balance, but don't worry about this terminology for the moment. So I just copied this equation. I just say, well, you have reversibility if q is equal to p, of course, and you have the same law, like in Newtonian mechanics. We just discovered we have to use the same force. Well, if you have the same law for updating, that's like reversibility, right? Okay. So that is to be remembered, and there is from here a small step that I want to add. Still, I'm still living within the brackets, but it is somewhat a small deviation that I want to add, and that is the following. So for the moment, what I have been saying in these 2 slides is what is a Markov chain, how it is determined, and what it means to be stationary. But in fact, I'd like to go, for the purposes of my models that I will be considering, it is advantageous and more physical for me to go to continuous time. Right? So the rate at which time flows, you can imagine, could have an influence. Remember that when I was doing this kind of PS, these postscripts, that there was always this constant in front. But that's basically a time constant, right? That's basically saying how fast is time running, right? So let me try to get that richness, and let me therefore, instead of trying to define, I could do it in discrete time, but it is less elegant. Let me immediately take a limit that I go to continuous time. So how do I do that? How do I go to continuous time? Well, it's kind of simple, but let me do it for my 2-level system, and then in general you will understand it. Okay, so let us look at this 2-level system, and let us apply our formalism of the Markov chain. So what do I need? I need the transition probability from 0 to 1, and the transition probability from 0 to 0, etc. I have, like, if I put a graph, it would be like this, no? I have 0 and 1, I can do this, and I do that. These are the transitions that are just by the lines that I'm connecting. Of course, I have to be careful in the sense that the probability to go from 0 to 1 should be positive, and the probability to from 0 to 0 should add up to 1. Just have to make sure it is. So in other words, the transition the stochastic matrix for my 2-level system is a 2 by 2 matrix, no? It's a 2 by 2 matrix, and in the convention, which is kind of logical, I hope, to go from 0 to 1, I could call it psi 0 maybe, and to go from 1 to 0, I call it psi 1, that's the number. And then what I should put here is 1 minus psi 0, and here I put 1 minus psi 1. Right? So what is 1 minus psi 0? It's the probability to stay in 0. So what is now the idea? So good to know this once in your life. Maybe you've heard it, but to hear it twice is also good. So look at these trajectories. What I would like to do is really that if I fix the time, it should be a finite time, that in fact a lot of discrete times have passed. So that these things come closer and closer together. It's like a continuum limit that I'm taking, right? It's like a continuum limit. So that somehow I can start to do something like that. That's what I would like to do. Something like that. I would like to go to really a step function. Instead of a discrete points, I would like to go to a step function where, okay, I'm not doing it very well here, but like that. So I really go to a step function where I'm staying in 0, and then I jump to 2, and then I stay in 2, jump to 3, etc. That's the kind of thing that I want for a continuous time process. So what does that mean? Well, intuitively, it means that I could stay for a long time. I want to stay for a long time. So I will take a delta, because delta I think I do not have. So I will add here the letter delta, and I will multiply these numbers with delta. So I mean the size, I multiply with delta. Delta goes to 0. So if delta is actually equal to 0, then I stay forever lazy in my seat, either 0 or 1, which is also not the most interesting life, but it's a good beginning to see the world, right? So, but I'm not going to take delta to 0 immediately. I'm going to repeat this very often, this updating. So what I'm trying to do to go to continuous time what I will do is I will take this stochastic matrix, which is now parameterized not only by xi 0 and xi 1, but also by this small number delta, and I will take it to a large power n. So this is, of course, as we saw here, doing a lot of updating. Then you're really starting to intuitively think about maybe something, I hope you have, well, maybe all of you know this very well, the Poisson. type of thing. No, you know that Poisson was a French mathematician, statistician, and he was interested in the casualties in the Prussian army. And you know there were especially, I guess, problems with the horses. That you know in them there was a bad accident with the horses, but there were very few, in the sense that there were many horses, but the very fact that there was a particular horse that was stampeding was very low. So it was a very low probability for an accident, but there were many horses and many years. Right? So this is the typical scenario for a Poisson limit theorem. Right? Maybe you know the central limit theorem. We will come back to it perhaps in a moment. But there is also something like a Poisson limit theorem. The Poisson limit theorem, I'm not sure whether I'll be able to produce it, but let me first do this calculation, and then let me see if I can do the Poisson limit theorem. So what is this? So this P delta, I hope, is equal to the unit matrix, because this is the one there. See the one? And then I have plus delta, because that's the delta, a matrix which I will call L. And this matrix L is just the one you see. Matrix L is the minus xi0, xi0, xi1 minus xi1. Right? So I think now it's time to do, we are doing 2 by 2 matrices, but I hope you will believe me that we can even do it for 3 by 3 matrices. Anyway, so what I'm going to do is to say that this is 1 plus delta, this range from this matrix L to the nth power. And now I will allow me to say that I will take n to infinity and will take delta to 0, but I will keep the n times delta to be fixed at a certain number which I call by accident time t. Right? Yeah. That's what I'm doing. So if I do that, then in fact the usual kind of exponential formula appears. The exponential now in matrix, it's not a number, but it's the same way of doing. So you get the exponential of t times this matrix L. But now t is continuous. Sorry, t is now just a parameter, a real parameter, which defines what we call in mathematics a semigroup. The semigroup of evolution of the continuous time Markov chain. Markov process. Now we have a continuous time Markov process, and that's called a Markov jump process. Just for the terminology, now we are going in the direction of Markov jump process. So the trajectories that I'm now generating are basically coming from discrete time simulations, of course, but they look exactly like I was predicting that it will be. Okay, there are some questions that you can ask, but I'm not going to answer them unless you ask them. What it means to say that you're here or should you be here? It's a convention. It's called, there is even a French abbreviation for that. It's called CADLAG, continuité à droite, limite à gauche. There's a convention to say what you do at the jump times. So now a continuous time Markov jump process is giving trajectories which are like the quantum jumps, no? The quantum trajectories are just like step functions, meaning piecewise constant. Piecewise constant generated by, if you wish, the Fermi golden rule up to the cutting off at the Born-Oppenheimer approximation, just to generate these stochastic trajectories. Is that okay? This is derivation is a bit looking algebraic or analytic. It's not quite probabilistic. Maybe some of you prefer not the algebraic way of doing things, but more probabilistic way of doing things. In that case, I would need to tell you the Poisson limit theorem, but let me tell it in words maybe. You know, the binomial distribution. So why the binomial distribution? Well, basically, you're counting the number of successes, but the successes are in terms of jumps. So when there is a jump, there is a success. But the jumps are very, imagine now that the probabilities of jumping, these probabilities of success go to 0. So it's very, very small. But the sampling, the binomial distribution depends also on the number you try, no? there are two numbers, the probability of success, like in the Bernoulli distribution, but also the number of attempts, n. So now take a lot of attempts, but with very low probability of success. So you take the binomial distribution, you let the number of attempts go to infinity, the probability of success go to 0. That distribution, that binomial distribution, is going to a Poisson distribution. And this Poisson distribution is what you're seeing in the jumps. And between Poisson events, there is the exponential time. So these kind of radioactivity counters here, these are like exponentially distributed, right? So the moments of quiescence or a distribution that are exponentially with a rate that may depend on the 0 or on the 1. Are you with me here? Yes, please.
So in that calculation, so this period is by any arbitrary Markov method. It is not necessarily that it will take me to a steady state.
No. Here it's nothing to do with the steady state. This is just in the construction of the simulation of trajectories. This is nothing to do with the steady state.
No, I will just question. So if I have a steady state,
yes,
then what should be that L matrix? Because if I take n into infinity, that would give me a diagonal matrix if I have a steady state. So how from here that I can go to that?
Oh, okay. So you're asking, how is it here that you're asking? So this is a matrix element, really, no?
No, I'm from here.
Here.
It is about TL.
Okay.
So, this is the operator. Right?
Yeah, L, by the way, let me take the opportunity to throw a bit more of a terminology to you. So this L is called the backward generator, or simply among friends, you can also call it the generator. That's called the generator of this Markov jump process. This is a matrix. Just a matrix in which all the information of the updating is there. As such, it has nothing to do yet with stationarity. However, you feel very correctly that you would like to connect it with what is stationary, right? Okay. So, okay, so let me answer that question for the moment shortly because I will repeat it. But let me go back to here first. I was saying it is time invariant, it is stationary, right? So how can I write a condition for rho to express that? Actually, I should have done that. Well, let me do the algebra in the following sense, that I take probability distributions as row vectors. Can you imagine a row vector? So it means I have states. So for example, I have rho S0 and I have rho S1. That are two numbers which make just a pair, a row. Now this thing P I can put as a matrix, as a 2 by 2 matrix, I can put here. And stationarity will mean that I get here the same vector for the same row. That's stationarity. Is it okay? So in that sense, I get that the the stationary probability is the left eigenvector of the transition matrix, of the transition probability. The same will be true for the L. Right? So in a way, we will write stationary distributions, and now I will be even a little bit more short than here. I will just think of this as a row. If I do here the L, what will it be, you think? It will be 0. Why 0? Because it's the ETL which is replacing the P. So if the P must be invariant, means the L must be giving 0. So this is in the stationarity. This will be the condition for stationarity, which is, of course, very important. I did not think that I would say that for the moment, but if you wish, I can say a little bit more about these things. What time do we have now?
20 more minutes.
20 more minutes. Okay, now let me try to understand what I want to say before I close the brackets. So, of course, let me skip for the moment more mathematics related to stationarity and all that. Let me not do that, otherwise I'm going away too much from the physics subject that I want to do. So at this moment, let me close the bracket. The bracket, you should not forget to close it. So here is my closure of the bracket. Okay, so that was just a mathematical introduction to some elements of Markov jump processes. I will erase this bracket now, and I will go back to my Markov jump process. And in fact, I should start by saying that, well, if I want to do a continuous time dynamics, I need to know this matrix L. But what does it mean to know the matrix L? That's basically to know the xi0 and xi1. So how do I find them? Right? Okay. So here we go. So you remember all the things here. And now I will erase. Okay, so just one more. So how do I get this mathematics now to connect with the physics that I have here? So I have a matrix minus xi0, xi0, xi1, minus xi1. I have this generator L, which is a kind of, okay, we know that it is important to generate a simulation of a Markov jump process. But basically, I have to know this xi0 and xi1, and what is the physical choice to do that? So what I really need to do is that I want to change my notation. That's the first important thing. So what is the xi0? It is really not a transition probability, but a transition probability per unit time. So it's a rate. So I speak now about the transition rates from k from 0 to 1, and the xi1 is a transition rate from 1 to 0. So these are rates. In other words, rates is like giving you more freedom because you don't need to normalize them. They're just probabilities per unit time. They are positive numbers, but for the rest, we don't care about. The relative values will somehow be important. Okay, but nevertheless, I still have to worry how should I choose them, and in particular, how should they depend on t and an epsilon? That's a physics question, right? So let me see how I could do that. But to think it's how to do the physics. Do the physics here, it is always a good idea to go back to the first page on our books of statistical mechanics. What is on the first page of our books of statistical mechanics is the microcanonical ensemble. So let us go to the microcanonical ensemble. Forget again for the moment the 0, 1, goes the two-level system. And there is something remarkable about, you know what is the microcanonical ensemble, right? The microcanonical ensemble, that is basically you fix the energy, and you think about the usual phase space as Boltzmann has taught us, where we look perhaps for a partition, a physical coarse graining of the phase space into what is called mesoscopic or macroscopic conditions. That would be our X. And we are going to ask for, in this microcanonical ensemble, we have a Newtonian or Hamiltonian dynamics. Right? So we have our fixed energy surface, and we consider trajectories from which are generated if you are giving here the momenta and the positions of all the particles. Then at a later time we just follow the Hamiltonian flow, right? Which is reversible, which is incompressible, etc., as you know in Hamiltonian mechanics. But as I said, we can also take a little bit more coarse-grained point of view, and we can ask in this microcanonical ensemble things which are related to probabilities, and the probabilities, of course, are defined in the microcanonical ensemble. And we can ask, for example, what is the probability that at time 1 we see something, and at time 2 or at another time another thing. So let me try. So we see X at time in1, and we see y at time 3, for example. Doesn't it? So I could ask questions like that. So what could it be? It could be that I have a room which is completely closed and isolated, mechanical system, and I could say that x could be that the particles are basically in this corner of the room with only few parts. I'm vague here, right? But just to understand, so x could be the condition of my room that most particles sit in the corner of the room, right? And let y be the condition that, okay, it's quite different. It's more like homogeneous that they are spread out. These are really two different macroscopic conditions. That's why. And I'm asking, what's the probability that at 1 p.m. I see this, and at 3 p.m. I see that? Okay, so how do I do that? Well, let me first tell you something which I hope is not paradoxical, that you understand. This is, of course, the same as the probability that I have y at time 1 and I have x at time 3. Do you agree with that? So the probability that at 1 p.m. I see that and at 3 p.m. I see that is the same as the probability that at 1 p.m. I see that and at 3 p.m. I see that. That follows from your answer you have been giving me 10 minutes ago, because Newtonian dynamics is time reversible. That's the time reversible. But that means that the probability to have, I hope your notation I can use, was the probability of y given x times the probability of x is equal to the probability of x given y times the probability of y. I'm just using the definition of conditional probability again. But what's the probability of x? Well, the probability of x is macroeconomic ensemble. So what we have is that the probability of y given x divided by the probability of x given y is equal to the probability of y divided by the probability of x. But that is, according to Boltzmann-Einstein postulates of the foundation of statistical mechanics, is just proportional to the exponential of the entropy corresponding to condition y minus the entropy of condition x per kb. Kb is equal to 1. Right? So such a macroscopic condition has a certain entropy. It means the volume of phase space corresponding to that region. And I just derived here from elementary fact that the transition probabilities, if I take them in reversed order, is given by the exponential of the change in entropy. If that is true, I can start to make models which are physical. So let me now go back here. I have here the K01 over K10, and I ask, well, what should I do? Well, here is the first guideline I get. The guideline is that if I divide this by that, it should be equal to the exponential of the change in entropy in the reservoir. That's an important moment in your life. Okay. Yes.
I have a question regarding the equality.
This one, yes.
Yeah. So the first, you have a configuration at earlier time that is X.
No, I first have to make it, no?
Yeah, you have prepared it.
I'm asking that I have it at time 1 and that I only want to have. It's not a conditional probability; it's a joint probability.
So yeah, that is. From X to Y, the transition is quite general.
Yes. So yeah, you're right. So the probability of X is very small, but that is very large. And here, this is very big, but that's very small. That's why they are equal. Right? So it's easy to go from here to here, but it's very difficult to make it. That's why there's an equality. Is it helpful? So you should not confuse it with the conditional probabilities. joint probability. So look at the trajectory, and I look at the probability of the trajectory where I first see all the particles in the room, and then I see them spread throughout the room. I see this trajectory. So I just entered the room, and I watch what happens, and I see this perfume spreading. And then I can say, well, the probability next day when I enter will be exactly the same, that it would go, the perfume goes back in the bottle. It's a bit paradoxical because the difference is between joint probabilities and conditional probabilities. I'm not saying, so the probability to make a perfume bottle is very low. Once I have it, it's easy to have the whole room full of perfume. But it's very low to make it, a perfume bottle. It's not easy to make perfume in a bottle. But if I have, like, I mean, that's the point that is not easy is exactly to go from Y to X. That's exactly the difficulty. In that way, they are equal. But it's just the expression of time reversibility. But now I'm using something, so is it clear? Because I know I'm also confused by such things.
It doesn't seem physical, actually. That's why.
Physically, I'm thinking physically, I thought. But tell me.
No, yeah. So this is a condition of detail balance, right? So
No, forget detail balance. Let's look at this equality. Is it painful?
a bit, I guess.
Tell me more.
No, I mean the configuration. Well, these two configurations are not. They're not equivalent. One is atypical and another one is.
That's absolutely true.
So okay, maybe I will.
So can you reiterate what you said about the last statement you made?
Yeah, so for the statement I made is a bit of an extrapolation, which requires steps, but at least it's a source of inspiration already. What I have derived here is that the conditional probabilities to go from X to Y given X, and the probability to go from Y to X given Y, that this ratio can be related to measurable quantities, namely to the exponential of Sy minus Sx. But what is it? It is the difference in entropy between the beginning and the end. So let me just blindly assume that in my two-level system, I should do the same thing. Of course, it's completely different because this is an open system. That's a closed microcanonical system. But I mean, let's be, opportunistic or something for the moment. Let us use that idea. Then what do I get? So it's called detailed balance, and it is now motivated from the Markov ensemble, but we could have mentioned it also before. But it sheds another light. So this ratio would be similar to that ratio, but it's also similar to what I had for our Markov chain. Remember, in the Markov chain, I had also QXY and PXY. Remember to say that they are the same. Ask time reversal invariant, I had to have that this is the ratio of the stationary probabilities. But no, the difference here is I'm not even thinking about the stationary distribution. I'm not even writing it. The only thing I do is physically, I have to write the difference in entropies. So do you get it right in your mind? So in the discrete time, I was writing the condition of detail balance. So the time reversal invariance of the stationary distribution in terms of the stationary distribution. But now I do not even need it because I have a measurable quantity. So what I will write here is the exponential of the change of entropy. What change of entropy? The change of entropy in the bath. What is the change of entropy in the bath? Well, I'm using now the Clausius relation that the change of entropy is obtained by the heat divided by temperature. What is the heat? Well, the heat is just this epsilon that I'm getting. So if I go from 0 to 1, I don't know whether it is plus or minus epsilon, so please help me. So this will be minus epsilon, I guess. Minus epsilon over T. I'm using again KB equal to 1. So this is already giving me something. Oh, I mean, this is enormously important that I now have derived, but these derivations, they all state from the first half of the 20th century, right? This kind of, but I'm getting here that the ratio of transition rates must be given by the change of entropy divided by the change of entropy, which is the heat over in the reservoir. That's what happens for the change of entropy. Okay, time is going fast, no? So, sorry, but I should have done one more calculation.
Actually, we started a little late.
Okay, but I'm not going to rush here, but maybe I will skip the how I do this detail balance for the harmonic crystal, for the harmonic chain, but I immediately go to an example of non-equilibrium so that at least we have done some non-equilibrium. Okay, I'll skip here the example for my, what I had this particle in the well there in the harmonic potential. I skipped what I do for detail balance, but I immediately go to a non-equilibrium example, which in fact combines the two. I will erase that with your permission. So now we go to the first example, but simple example. First example of how you do non-equilibrium calorimetry, non-equilibrium heat capacity for a non-equilibrium system. And as the simplest example, I have chosen the following. So I take a system of a particle. So it's again, you can think of the position of a particle, and the energy now is determined by another external variable, sigma, and the sigma takes values as plus and minus 1. So you can think of it as an internal degree of freedom or so, but you can also think of some experimentalist that is flashing the potential between two values. And the potential I'm taking will be of the same k as we had before. And now I'm taking here epsilon sigma times x squared. So that's the x, that's the same x. Sometimes I'm writing my x a bit different. So the epsilon is a parameter and k is a parameter. So what is this represent? This is like, we can call it indeed a flashing potential. Flashing potential in the sense that if sigma is equal to 1, you get a spring constant which is 1 plus epsilon times k, and if sigma is minus 1, it could even be repulsive in this case. You can flip between a stable and an unstable harmonic potential. Right? That is what is happening here. Okay, now the question that I would like to ask now is, how can we go about calculating the heat capacity? Okay, so let me give you, in the few minutes that I have without time to rush, let me tell you a bit of the initial logic that we would like to have. But before I do that, let me announce something that I will announce to be calculated next in Thursday. Or maybe you can try to do it already. To be calculated on Thursday is that here the stationary energy, so which means I have a stationary distribution. What is the dynamics? Let me, without much explanation, let me tell you what is the dynamics. So the x will change in time, and it will change in time because I take the derivative with respect to x, so the prime is with respect to x. Of course, it depends on sigma, right? So I should keep this notation. So derivative with respect to x, and then I will add something which for some maybe is mysterious, and I will have to explain that, but this is what is called white noise. And it is a force. This is a force, like minus u prime is a force. Maybe you like me to add here friction so that you understand that this is an overdamped dynamics. It's an overdamped dynamics where this is the force, but I'm adding a statistical force, which is a white noise, and which means that the correlations are delta correlated. So it is mean 0 and white in the sense that there are no time correlations at all in that force. but it has an amplitude which is put in front, which is in fact related to the temperature. So T is the absolute temperature. How I come to this dynamics, why this is physical, let me postpone this for the moment. Maybe some of you already know that, but I need to say it because if I say E is the stationary energy, that I must be able to say what I mean by stationary, and that is for that dynamics. Okay, I have not completed actually my dynamics, so that is how the X is changing, but there is also how the sigma is changing. The sigma is flipping to minus sigma at a rate alpha. By that I mean that the sigma is flipping between two values like in a two-level system, but now I call them -1 and +1. And I am at infinite temperature, so that in fact the transitions back and forth are the same rate equal to the parameter alpha. So now I have parameters alpha, epsilon, and k, and also the temperature. Okay, so I have a two-level system which flashes or induces the flashing of the potential, which remains harmonic. That's why it is simple and we can compute everything. Yes?
Just so we're at infinite temperature.
Boundary condition? Sorry, what did you say?
You said we are at infinite temperature.
Well, no. Here, so indeed, it's a good question. So for this flipping, we are at infinite temperature. You don't need to say that, but let me say that I wanted to relate it to what I said at the very beginning of the lecture, that there was a temperature there for my two-level system. So that is taking this two-level system, but as if it was at infinite temperature. However, this potential runs at finite temperature T. But the ingredient to govern its potential is an infinite temperature T. In fact, it's a non-equilibrium system, after all. We don't want to have necessarily everywhere the same temperature.
So this is one thing. But how do you define the temperature of a non-equilibrium?
Okay, so this temperature is the temperature of the environment. So I have, if you wish, two environments. I have an environment in which the particle is moving, which is a nice equilibrium. Well, nice. I mean, dead and passive, not very nice, but it's a temperature environment. I have a heat bath in which my particle is moving. And at the same time, it is influenced by somebody who is working on me. And the working is done with a rate alpha. So I have a work environment and I have a thermal environment. But indeed, I'm not defining the temperature of a non-equilibrium system. Okay, so I'm almost finished because I don't want to take much time. I just wanted to announce the following, that perhaps if you have the courage to do that calculation, which is not too long, you will find that this energy is in fact equal, and that's why I probably made a mistake last time also. The K is certainly not involved, it's just T over 2 wrong. Because either this is wrong or the previous one was wrong. Probably the previous one was wrong. But that's T over 2. So in other words, this is exactly the same, I hope, as for the equilibrium harmonic system. Right? Because there also it's supposed to be T over 2. You know, the equipartition theorem. However, in this case, the heat capacity will be different. So it can be that you have a stationary distribution which gives you the same stationary energy, but the heat capacity is different. And that's now the role of the dynamics. Yes, please.
You said the system is in an environment which has temperature T.
That's correct.
And on top of that, we are also doing work on the system.
That's correct.
Determined by radar.
Yes.
Then why is it that the average energy of the system, which was at equilibrium, and this
It's
was
not at equilibrium.
no, previously we did for a case where there was no external work.
Yes, yes.
So for that case also we had the same average energy.
That's correct.
In this case we also have the same average energy.
That's correct.
So what is the difference that the work is making?
The difference will be that there is a no different heat capacity.
So how is it that the energies are same? Like we are putting in work.
Okay, so this is so the energy is stationary first of all. So the work is doing work, but still you go to a stationary distribution. Okay, that's not trivial already. That's already a point you could wonder about. Is there a stationary distribution? In fact, there is a stationary distribution if epsilon is less than 1. Which I have not said so. Epsilon less than 1, there is a stationary distribution. Actually, it's not quite epsilon equal less than 1, but we will see what it is. And in that stationary distribution, indeed, this energy is the same as when epsilon is equal to 0. That's correct. No, is that a miracle? No, it's just trivial mathematics. But the miracle, or not a miracle, but what I wanted to emphasize is that even though the stationary energy is the same, the heat capacity is very different. There the work enters, as we will see next time. But in that sense, your question is very, very good, because that's exactly the surprise that I wanted slightly to emphasize. It's not because the energy is the same that the heat capacity is. And we will see non-equilibrium features here in this simple example. In fact, this is an example of a flashing potential in the sense that you can think of this that you have two potentials, right? One is like that, and one is maybe like that, and you're flashing between.
We have to modify the definition of heat capacity.
No, we don't.
If I do D, dt, then
It was not a definition. Do you get me or not?
in the previous case, it was like I defined it.
Yeah, I misled you, right? I misled you. So I was indeed using this definition, dE dt. But that's not a basic definition. This is a consequence of constant volume from the more basic definition, which is related to heat. Right? And you know that from the first law of thermodynamics, if you don't have heat, if isochoric transformation, constant volume, then this is the same. That's how it comes from. So one has to be careful. But there is even more than just that. There is more than that. I will have to explain that next on Thursday. Right? There are indeed many things I have to explain. But let's start by understanding that example. That will be the first thing. Is that okay? So anyway, if you want to prepare better for Thursday, I'm also here tomorrow. Right, I think. So if you have questions, I'm in room 308. So don't hesitate, just drop in, and if you have a point that you want to discuss, we can do that. So for now, thank you, and see you on Thursday.
Just 1 second.
Oh, there's a question online.
So is there any question from any of the online participants? If so, just unmute yourself and ask. Okay, looks like there is nobody, so you can close it.
Can I put the microphone here? Yes. Thank you.